I am trying some new streaming software to see if I can record lectures now that my previous software no longer permits it. So we'll see how that goes. I really won't know until sometime after class. Sometimes YouTube is not altogether prompt about putting up the link to the stream, so we'll see. Okay, so at this point, let's recap what we've done so far this semester. So it probably feels like ancient history now, but at the start of the term, you were building things like and, or, and not gates. Right. Then you went on and developed arithmetic, ALU, RAM. You built a CPU out of these components. And having completed that particular task, you then moved on to creating an assembler, and you've now just finished creating the VM translator. So at each of these levels, we've introduced some new type of abstraction to conceal the complexity of the level that lies beneath, right? So at bottom, you had NAND gates. You built some basic logic gates to manage the complexity of trying to express an idea only using NAND gates. The ALU was a way of creating a chip that lets you express arbitrary integer arithmetic, again, only using NAND gates. Now, the ALU was pretty simple, right? It lets you do adds and subtracts and some logic. But as we'll eventually see, if you can do those, you can eventually do multiply and divide as well. RAM, of course, was a very new kind of thing. RAM was about saying, I want to remember what happened. Okay? And then the CPU put all of this together so that you could have the idea of a program that changes memory over time in a way that is systematically controllable. But of course, the CPU only processes ones and zeros, and those are possible but highly unpleasant to program with. So we developed an assembler that took letters and numbers representing instructions and turned them into the ones and zeros. But even the assembler is kind of painful to deal with, right? You don't have a notion of a function, for example. And so we created this virtual machine language that then supplies the notion of a function and the notion of local variables and everything associated with it. So what remains is really in a couple of parts. The first thing we're going to work on after spring break, we're not going to start this till after spring break, is a compiler. And the idea is to take a program in a high-level language and turn it into this VM code. The other thing we're going to work on is a simple operating system. Now, this operating system is going to be pretty limited. Its main purpose is going to be, well, as with any operating system, the purpose is to let you interact with the hardware. But the specific focus of this operating system is going to be on the screen, and keyboard, and memory, and thinking about managing memory and the like. And we'll get to that really towards the end of the semester. So to prepare to do these things, what we're going to work on between now and spring break is writing programs in the language that our compiler accepts. And that's what we're going to talk about today. So that language they call Jack. And this Jack language is pretty heavily inspired by Java. It's going to be very, very similar to Java. Not quite the same, and we'll be going over a lot of the differences today, but it's going to have a lot in common with Java. Part of the goal here is to see how a language like Java gets mapped into the abstractions made available by the computer hardware. So what then characterizes a Jack program? What are the abstractions, generally speaking, that are available? So all Jack programs consist of classes. And each class is going to be in its own file. Ultimately, each of these classes will be translated into a VM file. So each class, they'll be generated a separate independent VM file to control it, to represent it. And then as you saw in the VM translator, all of those VM files get stitched together into a single assembly file, right? So what can we have within a class? So within a class, we can have methods and functions. And what's the difference? A function is not associated with an object. Every method has some attached object. And so this is similar to Java, where in Java there's a notion of a static method, which is akin to what they'll call a function in the Jack language. And then classes also have data associated with them. So classes, you create objects of the classes, and each object has a specified number of data elements. So far, it sounds a lot like Java, because it is. So how else does it look like? What other features does it have? So let's think about a block of code. So what are some things we're going to find within a block of code? Well, we have a notion of if-else, and we have a notion of a while loop. That's pretty much it for control structures. So we're not going to have a notion of a for loop, for example. Why do you think they left for loops out? Anybody? Yeah, Fee. Say that again?
Because you can make it with a while loop.
Right, you can emulate a for loop with a while loop. And so, consequently, there's no particularly deep reason to have a for loop. Now, for loops are great to have in a language, make no mistake. For loops, well, what is it that's great about having a for loop in a language, actually? Somebody tell me. Yeah, Andre.
Determine the range or the length of line. So you can't get stuck in a forever loop.
Right. What's great about for loops is they won't generally become infinite loops. Right. What a for loop does is it automates a lot of the work you need to do if you use a while loop to do a definite amount of iteration. If you know ahead of time this is the number of loops I need, a for loop is a lot nicer. But in principle, if you've got a while loop, you can do anything you can do with a for loop. So to keep the language simple, we're just skipping for loops entirely. Okay. Then we have commands versus expressions. So in a command, it begins with the word do, and then there will be something imperative that happens that somehow changes the state of the machine. With an expression, you calculate a value, and then if you want to bind it to a variable, you use the let keyword. So you say something like let x equal 5 plus 3, for example. So there are actually a fairly limited number of things that can even happen on a line of code. That's really most of the language. So here's something else important to highlight, and this is the case solely to simplify how the compiler works. We have kind of an undefined order of operations. So, in other words, when you're doing expressions, I highly encourage you to use parentheses. Otherwise, it'll probably just evaluate things left to right without any concern for precedence or any such thing. It turns out that operator precedence is actually rather challenging to build into a compiler. It's going to be hard enough as it is. So we're going to make heavy use of parentheses in any arithmetic expressions that you create. So then what about data types? Data types are, generally speaking, pretty simple. You have ints and booleans. I don't know what happened to my, there we go. You have, kind of ints and booleans, and this is going to be essentially that same machine word type you've been working with at the lower levels. And then we're going to have arrays, and then we basically have objects with strings being an object type, and so forth. So, in addition to all of this, the Jack language has a standard library. And that standard library is what you're ultimately going to build in Chapter 12. Okay, but the standard library is really, really important for getting the language to do anything interesting, like, say, I/O. So what are some aspects of the standard library that you're going to care about? There is a math module that has things like ABS, multiply, divide, and so forth. There is a string library that's got lots of little string functions. There is an output library, which is going to include extremely important things like printing. So you're going to be using the output library a lot. There is a keyboard library that includes stuff like readline to get input from a user. There is a sys library. I'm sure you're amused to know that sys will include a method called init, which you don't need to be calling. Just thought I'd mention in passing that's there. And but more useful is halt, stops a program execution, error, print an error code onto the screen and halt, and so forth. So all of these are listed on pages 190 to 193 of your book. So they're all there, they're all available. Well, as you know, it's a lot more interesting to actually look at a program than to hear about it. So let's look at some programs in the Jack language. So the programs I'm going to walk through are just programs that are actually test inputs for your compiler that you'll be working on in chapters 10 and 11. So here we have a first program. And what this program does is it lets the user enter some numbers, and then it will compute their average. So what does this program look like? Everything's in a class, and specifically, in every Jack program, there needs to be a class named main, and that class named main should have a function named main. So by declaring this as a function, we're saying this is not attached to any particular object. This class is just where it hangs out, kind of like a static method in Java. Void is the return type, which is to say it won't return anything. And then main is its name, and it doesn't have any parameters. Now, at the start of every Jack function or method, we list all of the local variables that we're going to be employing in that function. Unlike Java, we can't just declare a local variable right before we use it. We have to declare all of them at the very start of the function. Why do you all think this might be the case? Yeah, Spencer.
So it can reserve all the memory spaces for all of them beforehand instead of doing it at conception.
Exactly. We list all of the local variables at the start of the function because we need to reserve stack space for those variables before the function begins. So in other words, when a compiler comes along, it'll process this. It'll say, okay, there's a function named main, but I'm not going to generate the function instruction until I find out what all my local variables are. And so it's going to chug along and it's going to say, oh, there's 1, 2, 3, 4 local variables. So now I can emit the VM instruction function main.main 4 because there are 4 local variables. As we alluded to when we were working on the virtual machine, it's not like it's putting the entire array on the stack in the local segment. It's just putting a reference to it that ultimately, to access the array, that reference will be copied over to pointer 1. And then that'll let us access it using the that segment. All right, so we've declared some local variables, and this var keyword we have to use when we're ready to begin these declarations of local variables. Okay. So then, the next thing we do is we set up a local variable length, which we declared up here. So we want to set its value to be the result of the user typing in an integer. So we've got this readInt library, standard library function that does a basic input. How many numbers? We ask keyboard.readInt, and then we'll get it back as an int. On this next line, we create an array of the specified length. And so array.new parentheses length makes us a new array. Generally speaking, most classes will have a special function called a constructor, which will be labeled accordingly, that lets you allocate memory for an object. Then we let I be equal to 0, and this while loop, of course, looks just like Java. So we say while I is less than the length, we let a bracket I, here's our array, right? So we let a bracket I equal the result of that number, and then we add to our sum, and we add 1 to I to keep track of where we're at in the array. And then once I is equal to length, we're going to print the average. Here's that do instruction I was mentioning earlier. Anytime you want to perform an imperative operation, you use do. So in this case, we wanted to print something. So we say do output.print string, the average is, and then do output.printed sum divided by length. Now, there's no kind of convenient commas or string concatenation or anything like that. Whenever you're printing and you need to mix some data types, you have to use a separate print instruction for the different data types. Yeah. And then all functions and methods, even the void ones, end with a return. Why might that be? So that your compiler generates a VM return at the end and cleans up the stack properly. So that is a first basic program in Jack. Any questions so far? Yes?
You said whenever you do an imperative operation, you need to use a do.
Yeah.
What does it mean for an operation to be imperative? Because in this case, something like keyboard.readInt, it didn't have a do, and I would think it would be probably within the same realms as.
Oh, I see what you mean. Yeah, basically something that doesn't return a value, that you're not using a value from it, is what I meant by imperative. Because there is certainly something imperative about requesting an input and changing a value. I mean, those are also imperative. Yeah. So maybe not the best term. Yeah. Cool. Andre, did you have a question? Okay, no worries. So, that's all interesting as far as it goes, but what we really want to do, of course, is try the program out, right? So, let's explore what it's like to do that. Okay, that is not the correct window. Let's try another one. This looks more like it. So, we have, as you all know, the VM emulator, the compiler, the hardware simulator, the CPU emulator, and so forth, right? What we, of course, make the most of for this case is we're going to use the compiler to generate VM code, which we could then run in the VM emulator. And that in turn lets us actually compile and run a program. So let's try this out. All right, so I'm going to do jack compile. Got that. Oh. All right, so I run the compiler on the directory that I'm compiling. Ignore the fact that my solution to the compiler is just hanging out there. My own version of compiler. Anyway, so let's see what this produces. Specifically, within average, we now have a file main.vm. So let's run the VM emulator. We're going to load that file up. And so you'll get this confirmation message. No implementation was found for some functions which are called in the VM code. The VM emulator provides built-in implementations for the OS functions. If available, should this built-in implementation be used for functions which were not implemented in the VM code? You might be wondering, why is it asking this? This is all about Chapter 12. In Chapter 12, you're going to implement the standard library. And so this is basically saying, do you want to use your own stuff? Or since I can't find your own stuff, do you want to just have us swap in the stuff that works? And for this assignment, the answer then is always yes. You're always going to do that. Okay, so I'm going to turn animation off because I just want to use the program. And I'm going to run it. And up here, it's asking me how many numbers. So I'm going to answer 3. And now it asks me to enter a number. Let's start with 10. Now let's do 15. And now, what should it be, 5 or 20 for an easily computed average? 20. The average is 15. And then it tells me that main.main finished execution. So that's the process by which you're going to compile and execute your Jack program. Any questions thus far? Yeah, Andre.
What if you put the character?
Oh, let's find out. How many numbers? 1. O-N-E. Error 2. Program halted. Array size must be positive. So, what does this mean? Jack doesn't exactly have type checking. So, if I enter the number 1, it's going to allocate it as a string. And the variable is just going to store the memory address where that string happens to be. It looks like that memory address was high enough in memory that it looked negative. So there we were. Yes?
What if you put in a string that would correspond to a memory place that has a positive number? Is it gonna compile?
Oh, it already compiled. It'll happily run. Yeah, it'll create a nice huge array. Yeah, unless it runs out of memory, which always a risk, right? Right. Like I say, yeah, the compiler doesn't actually do any type checking. I mean, that too would result in a much, much longer assignment. Yeah. But it'll also make you appreciate type checking. Cool. Did you have a question, V? Okay. Yes.
What would happen if you enter like a float value instead of an int value for something like A or B or C? You know, when you say like
Oh, yeah.
3 numbers?
Let's find out. How many numbers? 34.2.
Ooh.
Let's find out. Uh-oh. I'm going to restart this.
That would be a big array.
Yeah. I just don't want to type that long. All right, just a second. What's that?
That's in computer science.
Yeah. Yes, the task manager. Yeah. We all love the task manager. All right, let's just restart it. Yeah. It never hurts to just restart. All right. So let's load this program. Yes. And oh no. I do not want animation. Yeah, there we go. So we'll say 3.2 numbers. Okay. Let's put in 4, 8, and 6. So it ignored everything after the decimal point. Yeah, this machine has no floating point capabilities at all. Now, in principle, obviously, we could create them. And typically, floating point these days is done entirely in hardware. So, back in the day, right, the 80s that I like to talk about so much, as I begin to be aware of myself as kind of a living relic, floating point was typically implemented in software in the operating system. But even in the 80s, the advantages of hardware implementation became clear, and they started creating chips which they called floating point coprocessors. So it was like you'd have a bonus CPU that just had some extra instructions for decoding and doing floating point arithmetic and its own ALU. And so whenever you saw a floating point, the CPU saw a floating point instruction, it would just ship it over to the coprocessor, which would perform the calculation. But yeah, there's a standard binary encoding for floating point bits, some standard circuit designs for them, and so forth. That's just outside the scope of this class. So yeah, that's how it'll handle that. Anybody else want to know how to break this? Because these were really cool ideas. And I love questions like this because it's asking about what's the scope and limitations of these programs. I mean, this is fairly good things to be asking about. Yeah, Andre. Oh, okay. Just fixing the baseball cap. Yep.
Well, it's more towards the VM.
Yeah.
How do you input strings like using the call?
Right. So it's going to call a library routine that's in the standard library. And in Chapter 12, you'll actually implement that. So ultimately, what you're going to be doing in Chapter 12 is you'll actually write it in Jack, and then it'll compile the VM. But you'll write code that looks at the keyboard memory and watches for the keystrokes to come in and then fills a buffer with each character one at a time, and then returns the memory location of that buffer. But yeah, we'll be working on that in Chapter 12. The VM language as such can't do it. and neither can Jack as such. Ultimately, we need to create it in terms of the machine, and that'll be chapter 12. So for now, we just let it happen. But essentially, that's how you're going to implement it. So another, related to that then is something like this keyboard stuff. Let me scoot back over here. Something like keyboard.readInt is just going to be yet another Jack function which gets compiled down to a VM function. And like there'll be keyboard.vm that contains function keyboard.readInt with some number of local variables. And so then it'll have a loop where it keeps looping as long as you haven't hit enter. And then just tries to pick up whatever digits it can find. I mean, we can really torture it if y'all want. Let's just find out what happens. So what if we run this again and I type 2F. Enter a number 4, 8, the average is 6. So what it did was it kept looping as long as it was getting a digit. And once it no longer had a digit, it just quit. Interesting. That probably makes it easier to imagine how you're going to implement it, right? You're basically just going to have a while loop, and while the character you're getting is in that 0 to 9 range, you keep sticking it into the next memory location where it's going to wind up. And there you are. Yeah?
What if you ask how many numbers and then you don't put anything, you just click enter?
Oh, let's find out.
So, yeah, and then you hit enter.
Oh no, did I?
Okay.
Okay. I forgot to tell it to rewind.
Yeah.
All right, how many numbers? Program halted. Array size must be positive. The array size was 0. So it just returned a 0
Okay.
and was like, I give up.
So the previous example, the reason why I gave you the ability to just keep typing stuff.
Yeah.
Is because you said 2F? And
Yep.
2F is not meaningful?
But 2 is. So it stopped at the number 2.
Okay.
Right. So if I were to run it again,
F2.
yeah, we'll try F2.
Oh.
Array size must be positive. In other words, it's on F and then didn't return anything. But then closely related, but the inverse, right? We could say, oh, whoops, stop, rewind. There we go. I could say 10E, and now I'll put in 10 numbers. And of course, division is just integer division. That's why I didn't get 5.5. Bless you. Bless you. Other questions so far? Let's look at another program and see what we can learn. So the next program we're going to look at initializes a new square dance game and starts running it. Okay, so this program looks pretty short, but of course there's going to be more to it than this. So in main.main, it creates a variable of type square game, named game. It says let game equal square game.new. So square game is looking like a user-defined class, a user-defined data type. New looks an awful lot like a constructor. And then we tell the game to run. And then after it ends, we tell the game to dispose. Now, what's the deal with dispose? Whenever you create objects and arrays, space is reserved for them in the heap. When you're done with the object, you need to tell the operating system that you no longer need the heap space. And calling dispose takes care of that. Now in Java, you don't usually think about this because the garbage collector running behind the scenes keeps track of everything that needs to be disposed. We're not going to write a garbage collector, and so we need dispose. Like, that would be a really fun thing to add to the class, but at some point we run out of semester. Yes, Caleb.
This may not be directly related to Jack,
Go for it.
but whenever you're writing to files,
Yeah,
you have to open them.
yeah.
If you consistently just run through the most of the negative program without ever closing the file, you
Right.
Where does that run issues?
Great question. And not unrelated, right? Because we've got the same notion of doing something then cleaning up, which is no doubt what brought that to mind. If you're reading a file, the only negative impact of not closing it is that no other program, while that program is still running, can open that file and write to it. So the operating system keeps track of every program that has a file open. So anytime you want to open a file, you say, operating system, please let me talk to the file. And unless some other program is writing to the file, the operating system typically says, yeah, sure. Or, if the file doesn't exist, the operating system says, no. So that's really the only consequence of not closing a file when you're reading it, is that other processes can't write it. So if you're done with it, it's good manners, so to speak, to close it, so that if something else needs to write it, it can do that. You may have actually experienced this sometimes, like if you've got some file open in a word processor or something, and then you try to move it or something, and then Windows says, sorry, I won't let you do that. That's the same phenomenon. Now, if you're writing a file and you don't close it, there's a very real risk that the stuff you wrote doesn't actually appear in the file. And the reason for this is that writing to a hard drive is an expensive operation. By expensive, we mean most operations in the computer are at roughly the speed of light, right? You're just shipping electrons around between circuits, which is what we've been doing all semester. If you're going to write to a hard drive, you actually have to send commands to the read-write head of the hard drive and the motor that spins the hard drive. So you've actually gone from the purely electrical world to the physical mechanical world. That introduces a huge time latency. So the typical solution to this latency is don't bother spinning up the hard drive until you absolutely have to. So in other words, when you write to a file, typically what happens is you're writing to a buffer in memory where everything you write just kind of hangs out there until you close it, and at that point it'll actually start up the hard drive and write stuff out. Now sometimes this isn't the case. Operating systems can occasionally be more aggressive. Like, for instance, if your program is sitting there waiting on user input, the operating system might say, well, user isn't doing anything right now, why don't I start up the hard drive and do a write, since I've got stuff in the buffer. The underlying point is that you don't actually know when the operating system is going to write that stuff to the disk. If you close the file, that guarantees it's being written to the disk. And hopefully that answers your question nicely. So what about the square game? So obviously there's more to it than this. So we're going to open square game and find out. And it turns out this is a program with 3 Jack files. There's main.jack, which every Jack program must have, square, and square game. So let's look at square game and see how it works. So here we've got our first object with state. So it's got 2 instance variables. One is square and the other is direction. And square is of type square and direction is of type int, and there's a handy dandy comment saying what the values are of that int. So here's how we declare a constructor. We call it a constructor. And then we actually have to give it a return type, which should be the type of our class. and then we can give it a name. So we don't have to call it new, but new is a really well understood name for a constructor. And so the constructor creates a new square object. So it initializes square, and then it also initializes direction. And then it ends with return this. So what on earth does that mean? So you might remember from Java, right, that this is always a reference to the object you're inside of. In Jack, every constructor call has to end with return this, because that's how you return the object that you just set up. So, in other words, don't think too hard about it, just always return this, and life will be good. And the life of the compiler writer will be that much simpler. Because, right, in principle, you could say, oh, it's a constructor, so I'm just going to throw return this in there at the end every time. It's more work for the programmer this way, less work for the compiler writer, and since ultimately you're going to be both, I think we're going to have some mercy on the poor compiler writer. So now we have the dispose method. So what does dispose do? Well, it tells the square to dispose itself, and then it tells the operating system to deallocate its own heap memory. So why this order of operations? If I tell the operating system to deallocate my own heap memory, I still have a pointer to this other square, which also needs to be deallocated. So I actually have to deallocate it first before I ask for myself to be deallocated. And that's how I have a well-behaved heap. Now you might think doing this is a real pain to keep track of, and you'd be right, and that's why garbage collectors are everywhere now. So it goes. Yeah?
So in square class, we need also to have another dispose method, right?
That's right.
I think that thing is recursive and now.
Oh, that would be bad.
Yeah.
Recursive dispose, very scary. I mean, I guess it's not so scary if you had like a linked list where you would ask the next one to dispose, and then, you know, if the next is null, you wouldn't ask it to dispose. And then once all of those disposes come back, you know, you just dispose yourself. So actually, you could do a recursive dispose, but you need to be really careful about the base case. Yeah. Okay, and then here is move square. And this is pretty sophisticated. If direction equals 1. So notice for comparisons, we just use a single equal sign. Same thing for assignments. How do we distinguish them? Let. An equal sign is only an assignment if it's part of a let. Otherwise, we're going to call it a comparison. One might argue this is actually somewhat more elegant than what Java does. You never need to mix them up. Can't happen. So if direction is 1, you tell the square to move up. So method invocations where you don't care about the return value, again, you always use a do. Yes?
Do you have a notion of a dot equals method? You know when you're comparing objects?
Oh. There is no dot equals method. You would have to invent it.
What if I need to check whether two squares?
It's just going to check whether they're at the same memory location.
And I use the two equal signs I need to implement.
Yes, you would need to create your own method.
Okay.
Yeah. So it goes. And then it's got this funny line, sys.wait5. So sys.wait is just a function to make it pause. And that helps keep the animation smooth. And then here's the run method that kicked everything off. So run has several local variables, or 2 local variables. It has a character, which is a key that's entered, and then a Boolean saying whether we should exit. See this tilde? That's the not, logical not in Jack. It's not the exclamation point, it's this tilde character. So while not exit, we wait for a key to be pressed. So while key is equal to 0, we ask the keyboard for what key has been pressed, and then we tell the square to move. So the square is just always moving in the last direction you gave it. And then here are key values for the different keys that control it. Q, Z, X, and then the arrows. So Q quits, Z and X make it bigger or smaller, and then the directions move it around. And then here we wait for the key to be released, and then it just keeps coming back through until we hit Q, which causes exit to be true. And that's the square. Or the square game. Yeah.
So are these values key code A1? Are those ASCII values for
Yeah.
Q?
Yeah, they're ASCII values. Yeah.
I see.
So then finally, let's look at square. So this implements the square. So this has three fields, X and Y for the location and size for the number of pixels. The constructor sets all of that up, and then it calls draw. So draw does graphics. So for your graphics, it sets the color to be true, and then does a draw rectangle. Why are the colors true and false? Because this is strictly black and white, right? So true means you're drawing, false means you're clearing. Draws the rectangle, and there we are. And erase erases the triangle by setting the color to false. And then here is increment size and decrement size. I mentioned, right, you can't trust the order of operations. Use parentheses. This is an example of what I mean. Now, you'll find that every single arithmetic character is always only one character in size. So like and is just a single ampersand, or is going to be a single vertical bar. That too is done to make it easier to write the compiler. I mean, actually, one thing you'll appreciate once you write the compiler is recognizing how many language syntax features are in place to make it easier to write a compiler, as opposed to easier for the programmer. It actually happens more often than you think. Because ultimately, somebody had to write the compiler, and that person is going to take a lot of shortcuts if they can. Yes?
Let's see how draw rectangle method is implemented.
Sure. Oh, that's chapter 12. You're going to create it in chapter 12.
Is it not built?
Oh, it is, but if I were to show it to you, I'd be giving away part of your last assignment.
Yeah.
Yeah. So yeah, you'll figure it out.
Because I was wondering,
Yeah.
like let's say in Java, every time I'm using a Java FX of some sort,
That's
you
right.
draw a rectangle line.
Right.
Like you can either have it implemented for in the library and then you call it, give it parameters,
Right.
or you can actually go ahead and build one by sort of maybe pointing out some dot somewhere.
Right. So what ultimately is going to be behind that is you're going to have a nested loop where you plot pixels directly into the screen RAM. That's how it's going to work. Yeah, Spencer.
Is it a one-to-one relation, like from Jack to a VM file, or should we make it to where Jack files like all go into one VM file, like we did for
Oh.
VM to?
It's one-to-one.
Okay.
Every Jack file becomes a VM file. And then the VM translator puts all the VMs together into a single assembly file. But we don't have to worry about that. Just run your compiler, let it generate the VM, and then just use the VM emulator. That said, if you're feeling ambitious, you can then run your assembler and then use the CPU simulator. Yeah, Andre.
Are there any document functions that like Python is using that
Oh yeah, yeah, like the, you're right. So those are all on pages 190 through 193. Yeah. You're going to want to look over those carefully, and you're going to want to use them a lot. So like there's a lot of graphics available. There's not only drawing the rectangle, you can draw a circle, you can draw a line or a pixel. And again, you'll ultimately be creating all of those. But for this week, you just use them.
So
Yes.
Can you use Jack to write like a kind of sophisticated program like tic-tac-toe game or some sort?
Oh, definitely.
Like, that really has a lot of interactions and
Sure.
complex class.
Yeah. Yeah. Nothing's stopping you. Right. So, cool. Other questions so far? Yeah, Andre.
Is there any areas that would be
It's kind of up to you. I'm not going to be real particular about it. That is, I want you to write a program that works with a well-behaved user. If there are certain common things where when you're testing your own program, it's kind of driving you crazy, maybe do a little error handling, but that's not the main focus of this assignment, for sure. So, right, so a Jack program enables you to make full use of everything this machine makes available. You know the machine pretty well at this point. So this project is about thinking creatively about something cool you can do on this machine. Questions so far about Jack before we start talking a little more and thinking a little more about the project? Yes?
If you wanted to create like a static method in this class,
Yeah.
how would I do it?
Just function.
Say, instead of method.
Instead
say
of method,
function.
you just say function.
That means don't give it a void. Don't give it a type, a return type.
Well, you always have to give it a return type.
Okay.
The return type might be void, but a function can have a regular return type if you want.
Can you say, let's say a function integer, I don't know, print number, something like that?
Sure. Now there's a print int in the standard library available, so that's good.
Okay.
But when you do the operating system, I mean, that's going to be at a low enough level of detail where you wind up specifying stuff like, what is the pattern of pixels that corresponds to this character? For the sake of your sanity, most of them will be provided for you, but I think you have to implement the letter A. Right? Because that's part of what the operating system does, right? Is if I type the A key, why does a letter A appear? It's because the operating system has a lookup table that says when that keystroke comes in, here's the pattern of pixels that the user is expecting. So yeah, ultimately you're going to create all of that, like at a really low level. Just not quite yet. So, let me talk a little bit about our schedule from here and what I have in mind for this assignment. Oh, whoops. All right. I'll tell you verbally what I have in mind for it, and I'll make sure the web page is up later today. So let's look over at our schedule. So today, then, we went over Jack. For Wednesday, by Wednesday of next, Wednesday is too late. By Monday, so I'm going to make this, I really meant this to be Monday. Notice that it's the 16th. Yeah. So I got a couple things to fix on the webpage. So by Monday night, I'm going to ask you to submit a document describing your project concept. And we're actually going to get started on that with the time that's left in class today. Then on Tuesday, I'm going to have each of you present just from your seat. You don't need to do a formal presentation. But I'm going to ask each of you to describe for the rest of the class what your concept is and what features of Jack you're going to need to implement the concept. On Thursday, class is going to consist of everybody running a demo of their program. So you're going to make the program run, come on up, plug into the projector, show off your program. And then you might get some feedback during the demonstrations that leads to some changes in the program. And so then I'll accept the final programs through Friday. But you should have something ready to demonstrate on Thursday. as debugged as you can possibly make it. Part of why I have this, of course, is that often when we go and we give a demo, suddenly we learn about bugs that weren't there before. And so I'm building in some space to fix those things up. Of course, the great news about all of this is come spring break, bam, clean slate. Do spring breaky things, then we'll come back and we'll pick up with building the compiler. So, I don't have really strict requirements about the program beyond the vague idea that I want you to do something interesting. Okay? And I've got the more specific idea that you should have some classes that have some state so that you're using multiple source files. Generally speaking, I want you to make use of what the language has to offer. And the reason for that is you need to get as much practice as possible with the language so that when you start to write the compiler, you've got a good grasp of what the language is like. So you don't have to go totally overboard on this. After all, you've got a week. So it doesn't have to be like a massive final project. But I do want you to have some ambition to it. I want you to create something that's interesting. It shouldn't all be a single giant block of code in a main, right? At this point, you've learned how to build larger programs. It should be broken into some different classes and such. It's fine with me if you, say, want to adapt a project you did in a previous class to run in Jack on this machine. I think that'll be interesting as you figure out how to adapt it and so forth. But it should do something interesting. Obviously, a really simple video game is super for this assignment, and very much in the theme of the course, as they call their website, From NAND to Tetris. They actually have an example, a program that you have to compile. One of the test cases for your compiler is Pong. So they actually have provided Pong as an example of a game. So don't do Pong. But if you want to do a simple game, I think that's a really nice thing to do for this assignment. So what I'd like you all to do from here is we're going to have a little brainstorming session. So we've got 9 people today. Okay. So what I want you to do is get some paper out and just write down every idea that comes to mind for a project without any consideration as to its practicality. So just think something that would be cool to do. So I want you to take about a minute and just write down every idea that comes to mind. Yeah.
Does the project has to have any sort of graphical user interface embedded?
No. You can do a command line program for this. All right, so I'm going to go around and I'm going to ask each of you to give me one idea. So, Innocent, what's one idea?
Something like a snake game.
The snake game. And whenever I ask you for an idea, don't give me an idea that's already up there. Jack.
A game that uses like you build a tower and the timing, so it chops off how much you fail to time it exactly on it, so it continues to build up. So it's sort of the timing.
A timing tower.
Yes. That's what
V.
So the screen looks like it's moving, but there are obstacles just kind of shifting frames, and you're staying still and you have to jump over those obstacles.
A jumping side scroller. Does that sound about right?
The what?
The dinosaur film thing.
The dinosaur thing?
Let's see.
Whenever you don't have internet, it pops up a little dinosaur, and then if when you press spacebar, it will start the game that is exactly what you expect.
Okay, but I died. All right. So good. Okay, so anyway, we've clarified that. Yeah. Sure. It's a neat idea. I think that would make a great project, actually. Andre.
something like a short Zork.
Yeah. Short Zork. So it's an interactive text adventure. Spencer.
Creates an appropriate D&D encounter.
Okay. Andrew.
Kind of a card game or like I was thinking of golf. I'm not sure if you've heard of it, but like you flip the cards and it's basically like kind of chance about like which ones you flip over and then you can peek at certain ones.
Okay. Yeah. Paxton.
Connect 4.
Connect 4. Caleb.
Maze Explorer game, I guess. Maze and maze.
Maze Explorer. Space Invaders. Cool. Any other ideas anybody wants to suggest? So kind of floor is open for other ideas that you thought were cool. Yeah. Battleship. That's a neat idea. Other ideas? Yes. Flappy Bird. Okay. Other ideas? Yeah. Tic-tac-toe. Other ideas? Yes.
Have you ever played that like burger game from that yellow guy who Stingy when he has like the burger? And
Awesome.
so like he has like I don't know how to explain this, but he's pretty much to show you like the bottom of the burger bun, and he like moves around and like start falling.
Oh, yeah. I can imagine this, right? So it's not unlike Space Invaders, except you're trying to get hit.
So you want to stack them.
Yeah. And so it gets harder and harder the higher it gets. Neat. I like it. So we'll just call it the Burger Game. Yeah. Cool. Other ideas? So, in general, whatever idea you pursue, I want you to take the mindset of, even if it's a big idea that you don't really have the resources to implement, what does a simplified version look like, right? You can always imagine ways to make the idea simpler and then come up with a program that does that. In fact, I almost recommend it because programmers in general tend to overestimate our capabilities. And on a machine like this, you're going to be overestimating them a little more than usual. Just warning you about that. Part of your experience with Jack is going to be running into oh, well, this is so much easier on a normal machine. So just be ready for that, right? Like, for instance, you don't have array list sitting there. Right, you don't have much in the way of basic data structures. Any data structure you want, you're going to have to build. So you have to take that into account when you're assessing what you're going to do. This is pretty bare bones. I mean, that's part of the fun, but just be aware of it. There's no intellectual property on these ideas. Like, you're welcome to pursue a concept that wasn't necessarily yours. You're certainly not welcome to use an implementation that isn't yours. But concept, that's fine. So for Monday, I'm going to be asking you all to just type into the Moodle text box like a short one-paragraph description of what your project is and what Jack features it's going to be using, basically. Again, I'm not super strict on what this looks like, but generally speaking, it should be interesting. It should use a couple of classes that have some state changes going. But beyond that, it's really just up to you. So like I said, in class on Tuesday, you'll be presenting your concept. I obviously would encourage you to have the concept done well before then, but you have to have it by Tuesday because then you're going to be talking about it. I encourage you to have it before Tuesday because you're going to be doing a demo on Thursday, and I do think you want to give yourself more than 2 days to write it. So I'd encourage you to come up with the concept sooner rather than later. And from there, yeah, that's basically Project 9. Cool. Any questions? Yeah, Paxton.
Does Jack have a random number generator?
I don't think so. No. No. Oh, you are, of course, then welcome to create your own random number generator. Yes.
Does that have a two-dimensional array of some kind?
No. You would build it out of nested one-dimensional arrays. Other questions? Yes.
How would I implement something like a timer?
So you would have some kind of, there's no threading. So you would have some kind of a main loop that looks at the, is there a way to look at the system time? Or do you just have to guess with weight? I think you just kind of have to guess on the timing. So it might be on the level of, you've got some main loop that's constantly running in the background, and there's some integer that's constantly being updated in that loop. And then you work out the meaning of the increments based on running the program and seeing how long it takes. Which is kind of lame, but there we are. Yeah. Yes, Caleb.
So in order to have something that is quote unquote have something that draws and updates, and you have to test it at the rate that you want to
Yeah. Yeah.
instead of throwing it.
Right, because there's no threading. And so the square program is an example of that. So, yeah, maybe we got enough time to run it. Yeah, let's try that out. So. Is my VM emulator still up? Yeah. Yeah, yeah. You can just look in the Project 11 test cases. So yeah, the way this one works then is it has a 5-second pause. So if we look back at its source code, yeah, in move square. Right there. No. Right, because of course this is a simulated machine, and so. I guess it doesn't have to be a simulated machine. If I gave you enough breadboards and everything, you should be able to build it, right? Anyway, it's all good. Cool. Any last questions? All right. As always, of course, contact me if you've got any questions about is this a good concept, what have you. Just keep me in the loop, and I'll look forward to hearing about what you got in mind on Tuesday.